Okay, so for this small section on C expressions, we just have a couple of things. That is a whole bunch of bitwise operators like bitwise OR, bitwise AND, bitwise exclusive OR, bitwise complement. That is in converting any 0 to 1. So for example, let's just take a look at this real quick. If you have a whole bunch of zeros and ones, so let me go back to a situation like this. If you have a whole bunch, let's say this is what we're trying to not or take the complement of. Wherever you see a 1, you convert that to a 0. Wherever you see a 0, you convert that to a 1. So this would, from right to left, this would read, if I complement this, I would get a 0, 1, 1, 1, 0 here, and then everything else would be 1. And so that's important because the very last one, if you have an int, that very last one is treated as the sign bit. If you have any kind of variable that's not unsigned, for the unsigned variables, this very last bit over here is not treated as a sign bit, but for regular ints, which is what let's say this is, a 1 over here would mean that this whole thing is a negative number. And there's a very special way of representing negative numbers, and it's called 2's complement, and that's what's used in C. So it's something that we will see in a junior level course called Computer Organization. This course, we don't really talk about it so much. We just sort of introduce this idea that you can have negative numbers and how they're represented, but don't really do much more than that. Okay, so the basic result is if you have a positive number and you not it, right, you use the bitwise complement, you're converting this 0. So if you have a positive number, this is guaranteed to be 0. If you not this, you'll get a 1, you're guaranteed to get a negative number. So that's why when you take the bitwise complement of any positive number, you'll always get a negative number. That's pretty close by, actually. Okay, shifting left is something that's useful. It might come up mainly because shifting left is a very efficient way of multiplying numbers. So in this case, shifting left 2 positions, that's what this is saying. So this is saying take this number, shift left 2 positions. That's just like multiplying by 2 times. If this were a 3, it would be like multiplying by 2 3 times, and so on. So this is a very efficient way to multiply by 4, just to shift some numbers around. Of course, you can always overflow and get into all kinds of trouble. So this, you have to know what you're doing when you're shifting. Okay, so once again, let me just go back and say if I shift left, what does that mean? That means the 1 goes here, this 0 goes here, this 0 goes here, and so on. Everything is shifted left this way, 1 position. And then if you shift left twice, that's like saying this goes 2 positions over, this goes 2 positions over to the left, and so on. Each bit is shifted. Okay, and then you can also do shift right, which is a very efficient way of dividing. So it turns out this is integer division, so shifting right 2 positions is same as dividing by 4, integer division, and so that's why you get a 1. Hopefully we won't see a whole lot of this because this is one of those things, it takes a little bit of getting used to, and it also really helps to have had the material in computer organization, because it's really something that's closer to hardware, not something that we use in, although it is available in Java, it's not something that we use in most Java programs. Java does have a lot of bitwise operators, pretty much all of the ones we just saw. Okay, so one last C expression is the ternary operator. Most of you probably seen this either in Java. Java has this, and so does C++. So it all came essentially from C. So the ternary operator, which is this operator question mark colon takes 3 operands. I guess it's the only one, I think. So there's a left-hand side of the question mark, right-hand side of the question mark, which is also the left-hand side of the colon, and then the right-hand side of the colon. So 3 operands. That's why it's called ternary operator. So the way this works is sort of like an if-else statement. It's not exactly the same. It's not exactly the same as an if-else. So the way it works is the first operand is a Boolean expression. If it is true, then the value of this whole thing, this whole expression, is the value of this first expression. If this Boolean expression is false, then the value of this whole thing from here to here, this whole line, this whole line starting from here to here, the value of this whole expression is equal to expression 2 if Boolean expression is false. So this is sort of like saying, if the Boolean expression is true, return expression 1. If it is false, return expression 2. Is it exactly the same? No. So the way this is used is you can do something like this. Int j is equal to, check if I is greater than 10. If it is true, j gets the value I minus 10. If this is false, j gets the value I plus plus, which is actually just I. But I is incremented too, so it's kind of confusing. This is a pretty complicated one. Personally, I try to avoid using ternary operators just because it's so confusing, like in this case. But a lot of C programmers love this. They use it all the time, and so you might want to at least be familiar with what this is supposed to do. And you might see something about this on a quiz, so be prepared. Okay, so let's move on to detecting and printing out error messages. So the way this is used is through the use of this variable. It's considered a global variable, though it's not exactly that. You can think of it as a global variable, an int, which is set whenever a system call runs into function. So, system call runs into an error. So let's say you call a function like open, right? And for whatever reason, you get a file handle that's negative. Well, then you want to see what exactly went wrong. What you can do is printf error is and use this global variable error number. To be able to do that, you need to pound include error number.h, errno.h, and most systems will initialize it to 0, but it's always a good idea to do that whenever possible. Whenever you want to detect an error, just before the code that might possibly set the error number to some value, set the error number to 0, call the, let's say, the troublesome system call, and then printf the error number. And if it's something other than 0, you know that something went wrong here. Okay, so the way this works is most C programs can check this variable, you have to do a pound include error number, set it to 0 before a function call, and after the function call, if the error number is 0, that means there was no error. So if you print out the error number and it was 0, this thing worked fine. If the error number is not equal to 0, the interpretation of the error depends on which function set the error. So it's not like every function has its chunk of values that only it uses. Okay, so it depends on what function you called here. In this case, open will set error number to a certain range of values, and some other function might use the same range of values. It really depends on which function. Check the man page for the function to see what the interpretation of those values are. So for open or create, these 3 system calls, there are certain errors that this function can set. For example, if it returns exist, that is error exist, that means the path name already exists and you cannot really create it. So if you try to create a file that already exists, yeah, you'll get this error. You get an is dir, means that you're trying to open a file, but it's actually a directory, and so that would be a problem. If you do not have the correct permissions, let's say it's write permissions only or execute only, and you open it for reading, yeah, you would get an E access error. Okay, so here is a slightly more detailed example. Before you start, of course, you need to #include error number.h, initialize error number to 0, and then call whatever function might be causing problems, and then check if the file handle is negative, which means this open function did not work. Then switch on this error numbers. Remember that switch works just like in Java. This whatever you pass in has to be something like an int. Essentially it should be int compatible. Same is true in Java and C. And then you can have a whole bunch of case statements. So what kind of things do you check in your case statements? You'd have to check the man page. For example, in this, for the open function, there's a whole bunch. I think there's more than this, but there's at least these 3. And you put those 3 at least, or maybe more or fewer, in the case statements. And you can put in a more detailed message that you can print out. Okay, so in this case, we would try to open a file, we check the error number, find that it is the E is dir. We get that from the man page. And then you can print out a message saying we tried to open a directory. This thing is not actually a file. That's /file, which we thought was a file, is actually a directory. Therefore, you got an error. Something like that. So now on almost every Unix system, including the Linux system that we are using for this course, we will have access to this library function called perror, which is a very handy way of printing error messages. So perror basically has one argument, and it's whatever you want to pass in. A lot of times you'll pass in argv sub 0, which is one of the arguments to main, and argv sub 0, remember, is the name of the program itself. So how does this work? Let's say we try to run this program, and the program is called test, and we run it using /test. This is what's going to be passed in as argv to this main function. Let's assume this is in a main function. So argv sub 0 would have /test. It will print out the /test as a result of this perror, followed by a standard string. So in this case, if you try to, for example, open a file that doesn't exist, perror, we will pass in a simple string, which is just the name of the program, and perror does the job of printing out the rest of the error message. So bottom line is you don't really need to do this on your own. That is, you don't need a switch statement to check for each error and print out an appropriate message. Instead of all of this, you could just use perror. It does exactly the same thing. The advantage of this approach, that is setting up your own error messages, of course, is that you can customize your error message, make it more understandable, more relevant to the user. A lot of the error messages, we may not be perfectly happy with, because it might be something like this: no such file or directory. Instead of that, you could say you tried to open. You could put in, instead of using perror, you could use a custom switch statement and say you tried to open this file, but it's actually not a file, it's a directory. Right? That is a little bit more meaningful maybe to the user than no such file or directory. There's one more function which is called strerror. I think I misspelled it. There should be 2 R's over, actually a total of 4 R's in strerror. And what you do there is you get the string, the standard error message, using strerror. So you can get the error message and then customize it and print it using your own printf function. So same idea as perror, but this is a little bit more customizable.